Quirk is all about quantifying information risk specifically for machine learning models. Machine learning is everywhere. We use it anytime we want to determine a pattern. We normally use pre-built tools or pre-built libraries. We don't always look under the hood to see what's actually going on. This raises the question, how secure are those machine learning models? How private are they? How trustworthy are they? How reliable are they? Otherwise known as the CIA triad: confidentiality, integrity, and availability. What if you had a machine learning model and you wanted to feed it through some sort of process and get back out the good, the bad, and the ugly? In other words, could you quantify the information risk? Or better yet, could you quantify it and then get out a better, more secure model? Quirk started from some pretty humble beginnings. We started with the least squares regression model, probably one of the most simple machine learning models. It focuses on minimizing vertical distance to a regression line and generally predicts the behavior of dependent variables. We picked this model because the extraction of training data is very easy. It's an easy target. So some things that you need to know about the base model that we used. It's got a high R-squared score, which you would expect from a least squares regression model. But more importantly, about 11% of the training points were within 0.5 units of the model. So down below here, you can see the training data on the left, and then on the right-hand side, you can see the training data in red, testing data in black, and then the model itself, which is just a line in blue running through those data points. Now, our first extraction method focused on creating a phony training data set by changing data points one at a time, and then testing them to see if the accuracy increased or decreased, and flopping based off of that. And what we found is that about 8% of guessed points were within 0.5 units of a training point. For extraction method 2, we changed random sets of points instead of changing them one by one, and we got slightly better results with about 10% of guessed points being within 0.5 units of a training point. So here, what you can see is method 1 on the left and method 2 on the right. The actual training data is shown in red and the guessed data in black. And the obvious thing that we see here is that our guessed data isn't reaching those outer regions of the actual training data sets, and we need a little bit of a bigger variance. So we started messing around with the variance, and by that I just mean, are you a little bit looser around where that model's going to be, or are you a bit tighter, closer to the line? And in fact, we found a pretty important correlation. So as you'd expect, as the variance goes up or as your graph gets looser, you aren't able to extract as much data. However, as it gets smaller, the area that points can fall gets smaller as well. So just by nature, you're going to have higher extraction rates. But more importantly, the thing to notice is that that base model benchmark is always going to bound the other two extraction methods. And it makes sense because you can't create data where there is none, you can't create meaning where there is none. So it makes sense that you would be bounded by that model. So although 8% might not sound so hot, when you're bounded by 11%, you know, you're doing pretty good. You're doing okay. From there, we took a bit of a strange detour. We were going to go to other regression models, but we branched and went to a classifier. So for classifiers, think more region of best fit instead of line of best fit. And we're trying to classify an object. So I prefer to see this in 2 dimensions. So we added a feature and just added the functionality to have however many features you want. But the important thing that we found is that the training data is hard to extract. It's no longer an easy target. And it's because when you have a regression model, you're going to get out values for that dependent variable. Those values mean something. They have meaning. Whereas in a classifier, your classifications have meaning, but really all they are is ones and zeros. It's a lot harder to get information or to glean information from that, or to know where to go with your model. So from there, we're looking for paths forward. We have many more questions. What other data is encoded in an ML model beyond subsets of training data? Can an adversary determine the type of model being used? Obviously, it's easy to tell between, you know, a regression line and a classifier, but can you tell between, say, a logistic regression and a least squares regression. What tools and tricks can be created to figure out these sort of things? Another good example would be, can you figure out if the model is normalized, or stuff like that. What sort of intricacies have gone into this model that make it unique? Can you create synthetic data and discard the real training data without sacrificing accuracy? So in other words, perhaps to protect the privacy of that training data, could you create a model that's obviously synthetic, equally spaced points that still has the same accuracy? And lastly, does using this kind of synthetic data increase resiliency against data poisoning? We've seen model poisoning happen in previous research, so I think it's important to always reach out and try to connect with what other people have done, which is the main driving factor behind that last question there. And with that, I hope you check back soon for some more information on Quirk.